Hello again. Today I want to run through the Node.js security releases for November the 27th, 2018. They were for Node.js 11.3.0, 10.14.0, which is LTS, 8.14.0, which is LTS as well, and 6.14.0, which is LTS, and also in maintenance. So these came out yesterday. They have a bunch of inclusions in them. They were actually fairly major releases. And the highest severity rating in there is high, not very high, but high, and it's high enough to warrant getting your things upgraded as soon as you can. So let's first have a look at how these security releases work. On the Node.js.org blog, there is usually a post that comes out a week beforehand. This is November 2018 security releases. Now this date has been updated. It did say the 9th, I think? No, sorry, the 19th. Originally, the post just had this section at the bottom that said security releases will be coming out and just some basic details about what's going to be fixed. And then you get this release timing. Then on the day of release, a post comes out for each of the releases that are made. So as usual, so I can click over to each of them and I can see, for instance, I've got the Node 11.3.0 post, and it's got details as you would expect for a normal release post. And it does have some information about the vulnerabilities. Each of these release posts point back to the original post, which is what I was looking at here. And this original post goes into more detail. So along with the links to the releases, it tells you what was fixed in there and what versions are affected by them. This is on the Node.js.org blog, or alternatively, at the bottom of that post, there is a link to a Google group called Node.js Sec. Let's just have a quick look at that, and you'll see that it's a low volume list. Myself and Michael Dawson mainly posted that. And so what we do is we post the original. So in here, we can see the original post, and then the updated post will come as a separate email, and you'll get these two emails. So if you're running a Node.js deployment, I would really recommend subscribing to the Node.js Sec Google group as via email. So let's have a look at what's included in these releases. We have 5 Node.js specific vulnerabilities, and then we have OpenSSL upgrades. Each vulnerability is assigned a CVE number, and these are universal numbers. That's common vulnerabilities and exposures. It's a big database that's shared, and you can Google that number, CVE 2018 12120, and you'll find information about it in a bunch of different places. So Node.js assigns these, and then we report them to the central database, and then that gets distributed. So the first vulnerability, CVE 2018 12120, is the debugger listening on the wrong interface by default. Then we have a denial of service with large HTTP headers, and that's 12121. And then we have a Slowloris HTTP denial of service attack, 12122, and I'll explain what that is when I get into detail here. And then we have hostname spoofing in the URL parser for the JavaScript protocol. That's 12123. And then HTTP request splitting. This is not the first request splitting vulnerability we've had, but it's the latest. So 12116, and then the OpenSSL upgrades. Let's dive into each of them in detail. First one we have is the debugger listening on the wrong interface by default. This was fixed and reported by Ben Nordhaus, who discovered it through the normal flow of activity in GitHub. Somebody reported a problem with the debugger listening interface. Ben investigated, found there was a vulnerability, fixed it, and then this got released. Now we've given it a CWE number of 419. That's common weaknesses and exposures. This is a database of different classifications. We've called it unprotected primary channel. Now this only impacts Node.js 6 because the debugger has since been replaced with the inspector. This impacts Node.js 6 only, as the debugger was replaced with the inspector in later versions. So we're dealing with a very old release line here. If you're using Node.js 6 and you use the debugger, then you'll want to upgrade for this. The reason is because by default it will listen on any interface on your system. So it'll open up a server port 5858 on any interface, and then any external device on your network or on your deployment network could connect to it and then run debugger commands, which is quite powerful. By default, it should be listening on localhost 127.0.0.1. The second flaw we have is denial of service with large HTTP headers. Now, this took a lot of work to get fixed, mainly because doing a test case turns out to be quite tricky because node streams are becoming extremely complicated. and we were getting all sorts of errors with streams on different platforms. So coming up with a test case of this actually stole a lot of the time that was required for preparing these releases. So this was reported by Trevor Norris some time ago. Trevor Norris was a TSC member. He reported this some time ago, and we've only recently figured out the best way to fix it that was going to cause least disruption and was standard. Matteo Collina submitted the fix for it. We called it a CWE 400, which is uncontrolled resource consumption, otherwise known as denial of service. It impacts all versions of Node, and what was happening was that the previous limit for total HTTP header size was 80 kilobytes. So you could start your headers and then submit 80 kilobytes worth of data, both in keys and values, before Node would say, hey, that's a bit too much. Normally, supplying lots of data to Node is not a big deal because Node is normally streaming. Unfortunately, with headers, there's this state buffering thing that happens where you can supply very large headers and keep on supplying data. So if you have a header that's a single, like a small key with a massive value, and you just keep feeding it data and you provide 80 kilobytes worth of data, then you can, as an attacker, you could determine when that data gets converted into a string in Node.js. Now, if you do that with enough connections to the same server and you time it right, you can do a lot of conversions at the same time, which could crash the server or just make it so that it's unresponsive. So it's the combination of the large amount of data, but also the ability to control timing of when Node.js does a lot of resource conversion that causes this one to be a problem. Now, this is mainly a problem if you are exposing Node.js to the world without anything in front of it. If you're using a load balancer or some other kind of proxying solution, it's very likely that they are already protecting for things like this. The default that we chose for this is 8 kilobytes, which initially came from the Nginx default. So if you had Nginx in front of Node.js, then you've already got an 8 kilobyte default anyway. It was rejecting that. Most load balancers are designed to deal with HTTP in a much more strict way than Node.js. So you're likely to get a lot more protection if you have some kind of load balancing layer anyway with Node.js. As I said, the new limit is 8 kilobytes. If you start supplying headers that go over 8 kilobytes, then you will, as a client, will be rejected and the server will never see your connection. To understand any of these things that have been fixed in Node.js, you can always go to the source code, look at the commits, look at the things added and changed, and you'll find out the details. In this case, there's a new test added called test HTTP max HTTP headers, and it has 3 test cases in it, test 1, 2, and 3. Now I'm going to look at test 2 because it's the most easily understood. Test 1 deals with sockets and some other obscure things. In test 2, what we do is we manually create a batch of headers, and then we have this final one which is called xcrash, and we fill it up with just data that goes just above the limit, which is 8192 bytes. So just fill it right up, and then we expect that to be rejected. We start an HTTP server, and then once we listen, we have a client, and when the client is connected, we write the headers. Now, there's a few things we expect from that. We expect the client to finish with an error. So the client has written its stuff, and then we expect it just to be rejected. We also expect the server on the server side to emit a client error event. This is a standard HTTP server event, which you may not be listening to, but if you ever want to listen to client requests that get rejected through some kind of error before they get to your request handler, you can listen to the client error event and get these. So we expect to receive a client error event with a header overflow code. We also expect that our server's request handler is never called, so it never gets up to the request handler. It gets rejected early, sent off. So that's the nature of this bug here. If you send just below the maximum amount of header data, then it'll get through. Just above, it'll be rejected. The next flaw is called Slowloris HTTP denial of service. Now, Slowloris is a old style of attack. It's been around for 15 years or so. This was reported to us by Jan Maybach some time ago and recently fixed by Matteo Collina. It's a complicated fix because it involves timing and buffering and all sorts of things. So it wasn't easy to get through. We've again called this a CWE 400 denial of service uncontrolled resource consumption. It impacts all versions of Node.js, so these changes are on every version of Node. So the nature of a Slowloris attack, you can Google this if you want. There's actually a pretty good Wikipedia page on it. Essentially, you are drip feeding many HTTP connections to exhaust resources. So you would open up a number of HTTP connections to a server, and you would just keep them open while expanding the number, and you drip feed them to avoid timeout. And the server just has to maintain all these resources, keeping them open. It's less expensive for the client than it is the server, and you can end up crashing a server or just exhausting its ability to handle any more sockets. Node.js is a streaming platform, so it's more difficult to exhaust Node.js. And what's more, this attack actually only impacts headers again, so it's similar to the previous one. But body content of HTTP connections, they're streaming. There's very little buffering going on unless you're doing it on downstream in your code. So having these connections open for a long time and being drip fed, much more difficult to attack Node on the client on the request body. But in headers, because we do a bit of state management, you can actually use up a lot of resources by keeping the headers open. There's already a timeout on just your sockets in general. That's called set timeout. So server.set timeout, and that works on the socket level. If the socket is silent for a period of time, default is 2 minutes, it'll just be disconnected and cleaned up. So that's already in effect. So you'd need to drip feed it more than once every 2 minutes. The headers timeout now is actually a strict timeout of 40 seconds. So if you connect to a Node.js server and you're feeding it data, you need to get your headers out of the way in 40 seconds, otherwise it'll be rejected. Fixing this has involved adding a new feature to Node.js, server.headers timeout, which is a value that you can read and set on any HTTP server. The default is 40 seconds. That's the time to get the headers out of the way. It's in the Node.js documentation. On each release line, the documentation should have details about headers timeout. You can set it and read it if you need to change it for your environment. If this causes problems for you, you could back it off. But just be aware that the larger this timeout, the more ability there is for downstream users to attack your services. The addition of a feature in Node.js according to Semver rules require that we bump the Semver minor version. So in all of these releases, they've all gone up by the Semver minor number. So instead of 11.2.0, we've gone to 11.3.0. Now, as with the other HTTP headers bug, if you are fronting Node.js with a load balancer, there's a good chance that it's already dealing with Slowloris better than Node.js is. They are designed to deal with these kinds of attacks. So if you have a cluster as well and the user can't control what server they're connecting to, there's less chance of being able to attack your service anyway. So load balancer is always a good idea with Node, not just for this kind of thing, but in general. Right, the next flaw is hostname spoofing in URL parser for JavaScript protocol. This is a funny one. We called it a misinterpretation of input CWE 115. It was reported by Martin Bajanic. Also fixed by Matteo Collina, who was very busy in this release. In terms of severity, I'd call this very low. I think we called it low on the release notes, but I just don't see this being a practical attack. This impacts all versions of Node.js, and what it requires to be an attack is for a user to be able to pass input unsanitized all the way down into the URL parser. And then for that parser, the results to be meaningful, where the host name portion of it has some impact on some downstream action. So there's multiple levels that need to be true for this to work. And again, it just requires unsanitized input from a user. And I think anytime you're accepting unsanitized input, passing it to Node.js APIs, and this goes for any system, this is true in Java or any system, you're in for a little bit of trouble. So you should always sanitize inputs, be careful what you're receiving, put limits around it, put character limits, all that sort of stuff to make sure that users can't just fool your system. As I said, this requires the output of URL parse, the host name portion of that output, to be meaningful, because what this involves is, we'll look at the release notes. If you pass a string that is mixed case, so the URL is the JavaScript protocol, so not HTTP, not FTP, whatever, it's JavaScript, and you use some sort of mixed casing, so it's not JavaScript all in lowercase, then you can fool the parser into parsing the URL differently than it should do. We can look at the test case to find out exactly what's going on here. So the commit is avoid hostname spoofing with JavaScript protocol. The fix is to just use the lowercase version of the protocol string that's found. There's two places where that would need to be changed. The test cases show that there's these two versions of URL parse that it wants to come in and be parsed the same. One is JavaScript all lowercase, and then you've got this string here, which is, it should be a piece of JavaScript. It should be resolved as a piece of JavaScript. This one here has JavaScript with a capital A. What we expect is for this to be resolved where you've got the path name, path, and href to resolve as a portion of this string, and the protocol should be JavaScript. In the before it was fixed, this would come out so that the hostname portion was resolved as this. So this would be the same, except hostname would be the host here. So you can see that an attack would need that hostname to be meaningful and not just null coming out of URL parse. So you'd have to imagine some kind of scenario where it's mixed in with other values and the hostname somehow is extracted and then passed on down and used to connect to something. It's a pretty obscure attack. It would require the attacker to know a lot about your internal systems. I don't see it as something that it would be easy to poke at and test your services. Is it doing something with a hostname? Perhaps there's a denial of service in here somewhere. Anyway, I don't think it's a big deal. On to the next one. HTTP request splitting. This was reported by Caddy Tettleman. And it was fixed by backporting something that was already on Node 10 and 11. So this was fixed a while ago, but I don't think it was seen for the flaw that it actually is, which is surprising because this is something we've dealt with a number of times in the past. And it's misinterpretation of input again. It only impacts Node 6 and 8, as I said. It was already fixed on 10 and 11. Now, HTTP, the protocol, is fairly specific about characters that are allowed. Node.js is very flexible. The historical philosophy has been Node.js is a toolbox, an HTTP toolbox that offers you tools to build HTTP services. And then you would build and use frameworks like Express and Happy, and they would do a lot more of the strict packaging around HTTP and the type of HTTP you're handling. So Node.js just offers you the tools, and then these downstream things do a better job of keeping strict. Unicode has been one of the biggest problems for HTTP parsing, both in and out for Node.js, and this is just another in a series of problems with relation to Unicode. In this specific case, it's the processing of the path option to client requests. So HTTP request and HTTP get. That if you call those things then and you supply a path option, the processing of that path option can be messed up if you supply some clever Unicode. So if we look in the code changes for this, this is on Node 6. It's a little bit different for 6 and 8. And this isn't actually the final version of the code that made it, and I'll explain that in a second. The original code that was removed tested for the lower range of bytes, so up to byte 0 to byte 20. If you had any of them in your path option, it would reject it. Otherwise, it would say, it would pass it on. There's some notes in there that foreshadow the future problems here. Now, if you go above the normal ASCII range into 2-byte Unicode characters, you get to do things like inserting new lines. So the attack here involves providing a path parameter that has new line characters that would split a client request into multiple client requests. So you could actually supply you should do an HTTP get with a path that does one get, and then it inserts some new HTTP protocol strings that would do 2 requests in one. So it would be to the same server because it's only path, it's not a host or anything else. Again, this requires unsanitized user input to come into your HTTP request. So remember, this is not the server, this is a HTTP request. It requires unsanitized input to get into your application in some way that inserts itself into the path option for an HTTP request that then goes out to some other downstream server that you could then cause to make 2 requests to that server. The second one being completely uncontrolled or in control of the person that injected that string all the way through that path. So there's a lot of steps again there, and it's only to hosts that your application is connecting to downstream already, so it's multiple connections on the same host. There's a lot of things about this that make this a difficult practical problem, but it's certainly something worth fixing up. So the fix involves saying that acceptable strings for HTTP requests are only within the single byte ASCII range of characters, so character 21 to 255. And if you go beyond that, then you're rejected. So you will actually get a type error. The problem with doing this within a release line of Node.js is if we expand the ways that errors can occur, it's actually a semver major. So this technically would have been a semver major, but to get around that, what we've done is we've implemented this security revert equals CVE 2018 12116. So if you run Node with that flag, then it will fall back to the original behavior. So what we're saying is throwing our hands up and saying, okay, well, we've got to fix up the HTTP protocol to make it more strict because there are too many ways to use Node's lax parsing and handling to cause security problems. So in this case, we're going to lock it down, but acknowledging that that may cause problems for users because perhaps people are legitimately putting Unicode characters in their HTTP request paths. That's possible with Node.js, and people could be doing it now. You could be sending emoji in your path requests, and you have a server that responds with requests to emoji paths. So if you are doing that now, then and you upgrade to these security releases, you would get type errors thrown in your application, which is a breaking change. Node doesn't normally like to do that, but we give ourselves permission to do it with security fixes. So if you start Node now with that flag, security revert, then it will fall back to the old behavior. Just be aware that you'd be vulnerable to this thing, but also that it's just not going to work from Node 10 and beyond anyway. So this has been addressed there. Last up, we have OpenSSL, and I think I'm going to do a separate video on this, but I will say that up front here that the vulnerabilities are just not that severe. I wouldn't get too panicked about anything in here. Node delayed bundling releases by a week, so OpenSSL actually released these a week ago. We assessed that these things were just not critical enough for users to need right away, and if you did need them, you could run Node against a dynamically linked version of OpenSSL anyway. So Linux distributions were probably shipping this last week, so you might have had this update already, but Node.js didn't bundle it until now. Node 6 and 8 run 102, and Node 10 and 11 run 110. There are two vulnerabilities in each of these that have been given a CVE number by the OpenSSL folks. One of them is the same for all release lines: timing vulnerability and DSH signature generation. And then each one has a unique one. So the first one is a timing vulnerability in ECC scalar multiplication for Node 6 and 8, and then a timing vulnerability in ECDSA signature generation in Node 10 and 11. There is actually a third one here that wasn't given a CVE number, and perhaps a fourth that could have been. They have a strange approach to assigning CVE numbers. We've taken the line of giving anything that could be said to be a security vulnerability a CVE assignment. OpenSSL draw this really, it's not a very precise line about where they will and won't. And I did challenge them on one of these things, and they said it was a line ball call, but in the end they decided to go different ways. It's something about if you need local access and the triviality is low enough. I just don't think the line's strong enough. So there's actually more than this in there, but even these ones are low severity. And these were fixed in the OpenSSL open source repository in the last few weeks. So these things have been public for a while now. We were going to be floating them in Node.js until they announced releases. I'd already put pull requests in and they were being merged, and they were going to go out with normal releases. But then they released these, so we bundled it all up together. All of these require local access to a server. They're all timing vulnerabilities. At the moment, they're fairly academic. I don't believe there's any proof of concept for any of these. And these are just part of a new wave. I think that we're going to see more and more timing vulnerabilities, just side channel attacks against hardware. So CPUs and looking for timing of calculations. So I just think we're going to see a lot more of these, not just in OpenSSL. Maybe we'll have a few come to Node soon as well, where we're exposing a little too much information that if you're able to view an operating system as it runs on hardware, you could extract information from that could make your system vulnerable. We did see that with Node.js with the hashwick vulnerability. Maybe I'll do a video on that sometime because that's still an ongoing saga. Anyway, that's it for now. That's it for my wrap up of the Node.js security releases for November. I hope you enjoyed that. Please leave a comment below if you enjoyed this and want to see more of this kind of content. Thank you.